some work today that I've done together with my current and past students. Like Hiroki/Howard, this is my first presentation at the OEE workshops. Unlike Hiroki, it wasn't because I had somewhere else to be. I didn't have anything intelligent to say about open-ended evolution, and that may still be the case, but I thought I'd bring some ideas that we've been working on recently to see what you think. Not surprisingly, I'm going to talk about the role of embodiment in open-ended evolution. This has already been mentioned several times now this morning, and I hope I have something new to say on this topic. Okay, so before I introduce some of our work in this area, I wanted to spend the first part of my presentation taking a step back and sort of thinking about where AI has been and where it's going and what the relationship is to open-ended evolution. So as a community, we've been working on this question of performance for 30, 40, maybe 50 years, depending on how you think about it. You give a machine a problem, and most of the time it does no better than chance. And if you're very, very clever, you can eventually figure out how to get this machine to learn. We had limited success with this process for a long time. Recently, we have surprised ourselves by making some great advances from the left to the right side of this vector, and we now have machines that for certain tasks can do better than humans. So I would argue we're kind of coming to the end of phase one of our understanding of how to create intelligent machines. So where do we go beyond this, right? We're at 99%. We don't have much further to go unless, as Tim was showing, which I liked his cube visualization. We add another dimension, which is, of course, we don't want just specialized machines. We want general machines. So now we have a two-dimensional plane, and I'm gonna use this geometric metaphor throughout the talk. As Rodney explained this morning, we're all victims of metaphor. Here's the metaphor that I'm a victim of. You can think of each point in this space as a particular machine or a particular algorithm. It could be a robot, it could be a non-embodied machine. It's a machine that does something, and it may do one or more things. The higher in this plane the machine is, the more things it can do, and the horizontal position of the machine is, on average, how well it does at those tasks. So again, this is a little hand-wavy, but just to sort of give us a space in which to move. The embodied revolution, which started again in the 80s, Rod Brooks is one of the pioneers here, as well as to add a third dimension where we can now start to think about a machine as more or less embodied. And again, I'm not going to be too detailed in how to actually measure where you are along this third dimension. It's just, as Tim was mentioning, we can sort of think about this as adding sensors or motors, becoming sort of more complex, more embedded in the physical universe somehow. So this is not anything new. This is just a way to think about where we've been as a community or a species, trying to think about how do we build intelligent machines and how do we move about in this space. So there's a debate now about AGI. So sort of AI is solved, right? So what else is there? Let's talk about AGI. As always, there are many in our community that argue that we can get to the top right of the front face of this cube, and that will be artificial general intelligence. With enough computation, enough computers, we can eventually get a machine that can talk to us and pass the Turing test and achieve AGI. I would suspect that most people in this room, if you even believe in AGI, believe that in order to approach increasingly intelligent and increasingly general machines, they're also going to have to become, gradually, increasingly embodied. So for most of us that work in robotics or embodied cognitive science, we're trying to find a way to move along this grand diagonal. Again, nothing really new here, just a way to sort of organize our thinking about this topic. Okay, so there's something special about this third dimension, embodiment, compared to tasks and performance, and I just want to take a minute to talk about this. Why is Baker Street of London so famous? Sherlock Holmes, right? Of course. Why should Baker Street of London be famous, but it isn't? Tim actually already gave you a hint. Anyone who went through the master's program at the University of Sussex should know the answer to this question, and if you don't, shame on you. So Baker Street was one of the research, I wouldn't call it a lab, but a hangout for Gordon Pask. Tim already mentioned Pask, a brilliant cybernetician, a very deep thinker, and at the same time a crazy tinkerer. He was an artificial life researcher before artificial life existed. Here's an excerpt from one of his colleagues' papers. This is not Randall Beer. This is another Beer, who was a friend of Gordon Pask. Together they created this electrochemical sort of soup, or this crazy device. They hung it out of a window on Baker Street and picked up noise from the street. This electrochemical thing started to vibrate and started to actually perform a function in response to audio signals. So it evolved a new sensor modality, something that Tim mentioned. So one of the most, I'm just backing up here, one of the most interesting things about moving from the front part of this cube towards the back is interesting morphological complexity, where we're not just adding new sensors or new motors, but we're adding new kinds of sensors and new kinds of motors. Okay. So I'm going to talk now very briefly about the philosophy of all this. I've learned from this conference that if you have gray hair, you're allowed to talk about philosophy. I've gone prematurely gray, so in order to make myself feel better, I'm going to prematurely talk a little bit about philosophical things. Okay, so this idea of sort of evolving more embodiment in the sense of discovering or evolving or growing new sensors and new actuators, why is that important? Because it broadens the kinds of physical phenomenon that we can perceive, where we could be an individual, it could be a species, in our case it could be human society. Philosophically, you could argue that science is our attempt to ever broaden our species' ability to perceive the physical universe. Whether that's evolution or not, I don't know. Engineering is ever broadening action. Given the things that we're learning about the physical universe, that gives us a broader scope of action to manipulate that physical universe. And to me, moving into the cube from the front to the back of the cube is the most interesting aspect of open-ended evolution, broadening our ability to perceive and broadening our ability to act. Okay, so again, back to this cube for a moment. As Tim was mentioning, we can move about inside this cube, and that's very interesting, but of course we want to think outside the box or move outside of the box. We can move from the left to the right side of the cube, but only up to a point, right? You can only be 100% accurate or optimal at a given task, so there's a limit to the right side of this cube, but there is no limit to the upper part of the cube or moving from the front of the cube to the back. As far as our species knows, we can keep broadening our perceptual abilities and broadening our actions and discovering ever new tasks that are meaningful to us as a species. So as far as we know, there is no back to this cube and there is no top to this cube. So moving backwards and up is, according to me, the sort of open-ended evolution. Okay. The question then becomes, how do we move about in this space? So I'm going to switch over now to a little bit of the nuts and bolts of our approach to open-ended evolution. You'll see that the embedded axis here, the left to the right vector is green. We know how to move from left to right. Given a specific task, with enough data and enough levels in a deep neural network, we can move very slightly from the left to the right. We can get better and better at that task incrementally. And this is why this inset axis is small. One way of thinking about being able to move confidently and successfully through this cube is being able to make arbitrarily small movements along any one dimension while not making big movements along the other two dimensions. So just to put this in context, you'll see that the other two embedded axes are red, which means we don't know how to move small distances up or into the cube without disrupting the left-right vector performance. The red vector that's pointing upward, it's red because we haven't solved catastrophic forgetting. So for those of you that work in machine learning and AI, if you pose to a machine or an agent multiple tasks, it can usually get slightly better at one of those tasks, and at the same time it gets a little bit worse or much worse at all the other tasks. So there's been sort of an explosion in the literature in just the last few years about this problem, which I think is us as a broader community in AI realizing that there are other directions to move in rather than just getting more and more accurate on your test data, right? Okay. In my lab, we're interested in figuring out ways to move an arbitrarily small dimension from a small distance from the front of the cube to the back. How do we take a machine and add a sensor, add a motor, make some change to the geometry or material properties of the machine, and not disrupt its performance on all of the tasks that we've exposed it to so far? So one way to think about this, I think, is it's actually really, really difficult to do if you start to think about it. And it reminds me a little bit of, if you're a student of the history of mathematics, the period in mathematics just before the invention of calculus. There was this growing realization that it was very difficult to think about or reason about or analyze arbitrarily small movements or increments along arbitrary dimensions. So one way to think about this, perhaps tongue-in-cheek, is can we develop a calculus for open-ended evolution? We all know that you can't make big jumps into space and expect increases in performance or ability or generality. We need to figure out ways to move small distances without disrupting everything else. And I would argue we don't know how to do that so well, and that's why open-ended evolution is so difficult. Okay, so in the rest of the time that I have, I'm going to just very quickly talk about 3 research projects. I don't have time to go down into the details. Happy to talk with you about this offline. How do we make a small improvement in morphology without disrupting the robot's ability to perform a given task? This is some really exciting work that was spearheaded by Nick Cheney, who's just joining us on the faculty at the University of Vermont. I worked with him on this. This is really, really exciting. This is basically his idea. We take a Carl Sims type system, so we're going to evolve both morphology and control. Imagine we have this robot in the population. It's able to move at medium speed, represented by the big arrow. It produces a child organism, a child robot that has longer legs. So we have a morphological mutation, and surprise, surprise, the robot falls over. We've made a small change from the front of the cube to the back of the cube, and we've made a huge movement downward. We've lost the partial functionality of this machine. That's what I mean about trying to move small distances without disrupting ability. So the idea that Nick came up with, which was built on other algorithms, was every time a robot in the population suffers a morphological mutation, you reduce selection pressure on that lineage in the hope that perhaps that morphological mutation is actually an innovation and just requires some time for control to readapt. This is an idea that's been around for a long time. It's been done in a lot of different ways. The reason I like Nick's approach to this is that it's not adding an additional hyperparameter. I don't have time to get into the details. But just to show you again this idea, we have a parent, it produces a child with a morphological mutation, reduced selection pressure, and after a while, maybe there's a subsequent control mutation represented by the red arrow that allows this robot to do something that the parent could never have done. So the parent with shorter legs, no matter how good its control system is, could never run as quickly as the grandchild that has a morphological change and a corresponding control adaptation. Okay. Here's a visualization of the results from this. If you've ever tried to re-implement Sims, there's a dirty little secret, which is basically what your system is doing, our systems included, is random search among the space of morphologies and maybe making slight improvements in control. We've got 6,000 generations of optimization time on the horizontal axis, and after 100 generations, evolution craps out. There is absolutely no open-ended evolution here, regardless of what your definition of OEE is. Nick did this work on NASA's supercomputer. Please don't tell them how much of their computational resources we wasted on this experiment. This is without morphological innovation. This is with it. Each colored line that you see here represents a lineage. Every point along that line is a robot. Points along the same colored line, they all have the same morphology, but different controllers. So you can sort of see these potential morphological innovations. Some of them pan out, some of them don't, and even with reduced selection pressure, they get killed off. After over 6,000 generations, we're still making improvement. We're not adding new sensor modalities like Gordon Pask and his successors did. We're just complexifying existing sort of morphology. So not true OEE, but at least a path in that direction. We can move into the cube a small distance and only move a small distance up and down, only perturb the robots in that lineage performance a small amount. So going back to the calculus metaphor, this is almost now starting to think about partial differential equations. If we make a small change along one of the three dimensions, how much change happens along the other two dimensions? It's just one experiment, but hopefully is opening up a path to think about approaching OEE in a different way. Okay, I'm running out of time. I won't talk too much about this. There's the URL. You can go play Twitch Plays Robotics on your own time. This is inspired by PickBreeder. As Ken mentioned yesterday, we can kind of create open-ended evolutionary systems. In this case, it's robots grounding more and more human language. But we have humans that are proposing language. Language becomes fitness functions. So we have an open-ended system here. Again, you can go play it on your own time, but we still have humans in the loop. So it's open-ended, but not automatic. And I agree with Ken. We don't really know how to do that yet. Doesn't mean it's impossible. Okay. Here are 10 of the robots that have been evolved inside of Twitch Plays Robotics. You'll notice the sphere bot there, item E. The crowd issued the command move to the sphere bot, and it starts rolling. Everybody on the system agrees that rolling or moving away from the origin is move. The starfish bot, which you see in panel F, sometimes it moves away from the origin and everybody agrees that's move. Sometimes it jumps around on the spot and people agree and disagree about whether that is actually move. So it turns out that different morphologies allow the crowd to help the robots ground language differently. Symbol grounding problem has been around for a long time. Morphology matters. So there's another coupling between movement along these three dimensions. Last thing, I'll just show the video. It turns out we got a very nice simple result by Joshua Powers. I don't know if he's here, but he's here at the conference. Turns out that certain morphologies resist catastrophic forgetting better than others, which means different morphology means different horizontal cuts through the cube. And if you're in the right cut, you can move up without moving far to the left. You can resist catastrophic forgetting. It's another interesting coupling between these three dimensions of artificial intelligence. Okay, I think I'm out of time, so I will just, again, thank the people that did all the real work and the interesting work. Thank my funding agencies, and I'm happy to take a few questions. Thanks very much.
Let's do the same again. So form a line if you have questions here, and we will.
Interesting talk, thank you.
Thank you.
It seems to me your three-dimensional space could be, we could add a fourth dimension, which would be, I think a natural one would be sociality.
Okay.
Being embedded in some kind of society and contributing to the society. And actually, more generally, I think open-ended evolution would be going from an n-dimensional space to an n+1 dimensional space.
Sure. Yeah, I think that's a great question. So again, in this talk, we just addressed these three dimensions, which I'm more intellectually comfortable with, but there's no reason why, again, we couldn't add other dimensions. And again, think about if we want to slightly increase the sociality or the positive social impact of our systems, how do we do so while they retain their ability to do so? What would be the coupling among those four dimensions? I think that's an interesting way to think about things.
Yeah. So the one dimension that where you have performance, that's where you have optimization.
Correct.
The other ones are where you actually add new stuff in one way or another. Either ask the system to do another task or move new sensors or motors and expand the space.
That's right. Correct.
So, as I understand, there's a goal to get the true intelligence, artificial intelligence. You think that embodiment is the key. I think is that what we like by now is open-ended intelligence, basically. So all the tools that we use now are hard-coded, more or less, and we optimize. So you have neural networks; they are fixed or they just mutate a bit, but it's constrained in its own design. Or we use genetic algorithms or something else, but it's all very constrained. So what we lack is the ability. That's my theory.
Okay.
I would like somebody to disagree or say it's not true, but like what I think is one part of the constraint is that we have very like specific tools, and we are trying to make it reasonable. We are trying to make it like conscious, which is impossible. The other part that is missing is that we are using this silico.
But do you have a question?
Yeah, so I want to ask. Do you think that the problem is on that side that we are not using open-ended intelligence instead of? I'm not totally convinced that the embodiment is the key, but the way we try to use the intelligence.
Okay.
I think I understand your question. So personally, I believe it is the key, but I know I'm not, that's may not be the case. Right? What I'm hoping is that this kind of thinking and this workshop about open-ended evolution gives us a way to think about those kinds of questions. So someone would just mention there may be a fourth dimension. It may not be embodiment. What route do we travel through a high-dimensional space of algorithms and machines where we make small incremental improvements as we move through that space? And we should all be trying as many paths through this space as possible, and whoever gets to the upper grand diagonal wins. We'll see. We'll see. Mother Nature will decide, not us.
Okay. Thank you, Joe. It's a great talk. So you shared with us a little bit of dirty secrets about the blocky stuff, and
Yes.
the majority, I mean, the substantial part is random search, right?
Correct.
And then I wonder why then you illustrate this whole process as a continuum. Isn't there shouldn't be more discreteness or jumping around type stuff?
So the idea is you need to create an algorithm that allows you to move in a particular dimension through the space, right? This is the revolution in deep learning, right? Is actually figuring out how to move along the gradient of error carefully, right? That does not exist along the gradient of tasks, right? You can't gradually add a task and not disrupt things. So it's, I guess the better way to think about this maybe is points in the space are machines, and algorithms are able to create paths through this space. And since we've lacked one that allows us to move into the cube without falling to the left.
So we want to have this kind of smooth transition.
Correctly, correct.
Thank you.
Moment.
Very interesting. I'm wondering about, well, it's clear that you're using embodiment and you believe that embodiment is really a requirement to get the kind of open-endedness that we are aiming for. One of the things that embodiment gives you is a way to actually define tasks.
Yes.
And the language you use when you talk about tasks, though, is like you're giving it tasks. And I think one of the interesting things about embodiment is that embodiment can create new tasks. And it may be that you make a little change in embodiment and actually open up a whole bunch of new tasks.
Sure.
So it's not necessarily a little incremental change. I was wondering if you could comment on this relationship between embodiment and task creation or functionality creation.
Sure.
So I didn't have time to mention it, but if you look carefully, I've ordered these tasks vertically in the non-embodied space. So these are all machines that are just inside a computer. And then when we switch to the embodiment side of things, the order of these tasks change. So this isn't necessarily task creation. Clearly, if you don't have hands, you don't have manipulators in any way, you can't do object manipulation. So the moment that something like an appendage evolves, that creates the affordance or it creates the possibility of object manipulation, for sure. Some of the more interesting tasks are those where it's not clear that embodiment will help, and NLP is probably one of those. So there is the most heated debate about embodied and non-embodied systems is NLP. Can a non-embodied system understand natural language processing, or do you require experience with the physical world to be able to ground language? And again, this is a matter of debate, but clearly embodiment changes the order in which these tasks might be learned or evolved by a machine, and task creation is also a part of that.
So we have to switch to the general